Hey everyone and welcome back. In today's video, we are diving into one of the most important sets of principles in software design, the SOLID principles, and how they apply specifically to C++. Whether you are working on embedded systems, high-performance game engines or modern desktop apps, understanding SOLID is crucial to writing clean, maintainable C++ code. Let's get into it. So, what is SOLID? SOLID is an acronym. Each letter stands for a principle that helps developers build systems that are easier to understand, change, test, and extend. These are S. Single Responsibility Principle. O. Open-Closed Principle. L. Liskov Substitution Principle. I. Interface Segregation Principle. D. Dependency Inversion Principle. Let's break each one down, see how it works in C++, and why it actually matters in the real world. Single Responsibility Principle. This one is simple but powerful. A class should have only one reason to change. What that really means is, a class should only do one thing, and do it well. Let's say we have a class like this. So this report class is doing two things: generating report data and handling file input-output. If requirements change for saving files, say we now need to support saving to cloud storage, we are forced to change this class even though the generation logic didn't change at all. Instead, we should refactor like this. Now each class has one reason to change. This leads to lower coupling and better reusability. In C++, this also helps keep header files lightweight and compile times faster, which is always a bonus. Open-closed principle. Software entities should be open for extension, but closed for modification. That means if we need a new behavior, we should extend the existing code, not rewrite it. Here is a common anti-pattern. This design is fragile. If we add the triangle, we must modify draw shape. That's not closed for modification. A better way in C++ is to use polymorphism. Now, if we want to add triangle, we just create a new subclass. No need to touch the existing drawing logic. Open-closed works beautifully with virtual functions, but also with templates for zero-cost abstractions. Liskov Substitution Principle. This one is a bit trickier. Subtypes must be substitutable for their base types. So basically, it's valid C++ to create a derived object and assign it to a base pointer. But then, derived should behave in a way that doesn't break expectations. Here is an example that violates the principle. Now, if we write code that expects rectangle, this breaks if R is a square. Because the width and height are always equal, we have violated the principle. The takeaway: inheritance is not just code reuse, it's a contract. You must honor the base class behavior. In C++, this is why we often prefer composition over inheritance. Interface Segregation Principle. Clients should not be forced to depend on interfaces they do not use. In C++, this means we shouldn't create fat base classes with dozens of methods. For instance, this code. Let's say we now have a robot class. It needs to work, but doesn't eat or sleep. Now we are forced to stub those out. A better approach is to split this into smaller interfaces. Then a robot only implements iWorkable and the human can implement both. In C++, this keeps our object model clean and compilation units minimal, which helps build performance and code clarity. Dependency Inversion Principle. High-level modules should not depend on low-level modules. Both should depend on abstractions. This principle is all about decoupling. Imagine we have a report manager that directly creates a PDF exporter. Now, report manager is tightly coupled to PDF exporter. We can fix this using an interface. Now, report manager doesn't care how the report is exported, only that it can be. In C++, we can pass these dependencies via constructor injection or setter injection. And we can also use templates when we want to remove the runtime cost. So now you are all probably thinking, this is all great, but why does this matter specifically for C++ developers? Well, here is the thing. C++ gives you all the tools to write rock-solid architectures. Templates, classes, RAII, inheritance, lambdas, you name it. But with great power comes the ability to make a mess very quickly. Solid gives you a mental framework to keep your code modular, testable, and future-proof. It helps reduce compilation dependencies by isolating responsibilities. It allows you to unit test components in isolation. And most importantly, it helps you write code that your future self or your coworkers won't hate. Even in performance-sensitive systems, like game engines, applying Solid in smart ways, like using data-oriented layouts or compile-time interfaces, can lead to better design without sacrificing speed. Alright, that was a deep dive into the Solid principles in C++. Each of these principles helps build a small piece of maintainable architecture. And when you apply them together, the result is powerful. If you are building real-world systems in C++, don't just think about how to write code. Think about why you structure it a certain way. That's it for today. Thanks for watching, and if you found this helpful, don't forget to like, subscribe, and check out the rest of the C++ series.